So I'm here at the NASA Langley Research Center in Hampton, Virginia. I'm an acoustician working in the Applied Acoustics branch. We also have an aeroacoustics branch. We do a lot of different projects, mostly focused on aeronautics. So I've supported the commercial supersonic technology project with the Quest mission and the quiet supersonic X-59 aircraft. And recently I've actually been working more on the revolutionary vertical lift technology project, which is focused on all these new electric vertical takeoff and landing vehicles, or eVTOLs, and trying to characterize the noise and the human response to those. So that's the main focus of my work these days.
Welcome to the SCL podcast, filmed in the MD Acoustics anechoic chamber at their testing facility in beautiful Gilbert, Arizona. Today we welcome Aaron Vaughn, a Research Aerospace Engineer at NASA Langley Research Center in Hampton, Virginia. Aaron's work specializes in psychoacoustics and how humans perceive and respond to noise generated by emerging aviation technologies. His work is particularly relevant to NASA's AAM initiatives, or Advanced Air Mobility, where understanding community noise impact is crucial.
We're grateful for your time, and it's been a while since we've tried to connect with you, so we're excited to have you here. So talk to us a little bit about, let's see, we see a scale of the X-59 behind you there. What is that?
Yeah, so that's a 1/60th scale of the X-59 aircraft. It's actually been built. It's undergoing ground testing. It's X-plane that NASA's developed with Lockheed Martin to demonstrate quiet supersonic technology. So there's been decades of research on this area, and we're trying to collect the data necessary to, potentially inform the regulators to replace the current ban on overland supersonic travel and replace that with permissible noise standards. I haven't done anything specific with the aircraft. I am actually on the survey side of things with, we're going to fly this aircraft over communities in the United States, and we're going to collect human response data. We're going to see, how loud is it and how annoyed are people, and we're going to collect that data and send that off to the regulators for them to make the decision regarding regulation. But we have that technology that we believe is viable to reduce the sonic boom to a much quieter sound, such that it will be like a car door down the street that's closing rather than, a car door in your face slamming.
I have to ask some questions. One of the things I want to know is, obviously you work for NASA, and I don't know about you. When I was a kid, I actually grew up outside of Cape Canaveral, and then outside of Houston. So NASA, that's what we did every summer. We went and saw stuff with NASA. The question I have is, did you always want to work for NASA?
No, I did not have this as my, ultimate career goal of making sonic booms quieter. It was something that, step by step, it kind of fell into place. In high school, I was really passionate about music, and I played the trumpet in just about every music group I could, from orchestra to marching band, jazz band. I was musical pit. I was playing my trumpet everywhere I could. And senior year, I had some less than successful auditions that made me reevaluate and realize that I didn't actually want to pursue a career in music. And so, like most failed musicians turned scientists, I went into acoustics. I've loved science since I was little. I've always had a deep admiration for NASA and space. And my mom and my oldest sister were both junior high school science teachers. So that was something that, was influential on me. And my 8th grade science teacher, Mr. Tran, definitely inspired me to really enjoy science. And so when I entered in at Brigham Young University as a freshman, I entered in as a physics major, which actually my mom was a physics major as well. So I started at BYU, and they sent out an email to all the incoming freshmen all the physics students saying, hey, there's an acoustics research group that meets every week. And I was like, hey, that sounds interesting. My cousin, he actually participated in the program. He works for a hearing aid company. And so I was like, hey, I'll go check it out. And from there, I eventually got involved with research with Dr. Kent Gee and Dr. Tracy Nielsen. I was doing jet noise research. And from there, I continued in grad school with Dr. Gee, and I got my master's. And it was actually at an Acoustical Society of America conference where NASA had organized a sonic boom session that I first heard about this position that I now fill. So yeah, from there I applied and finished up my master's degree and started just about 5 years ago here at NASA.
Well, shout out to Mr. Tran and all the other teachers out there. I mean, I love that you kind of went back all the way to like a high school teacher and said that's what kind of pushed you as you kept going, right? Like, I have a lot of family that are teachers, and so it's, you know, sometimes it's a thankless job, right? But that's really cool. I mean, sonic booms are something that's always fascinated me as a kid, especially, and now the idea that you could potentially make it sound like a car door, that fascinates me. And is there anything you can kind of speak on how that is possible?
A sonic boom occurs when an object goes faster than the speed of sound. Essentially, the sound can't move faster than the object, and so all that pressure builds up, and it creates that step function, that shock wave. And so the sonic boom that you hear is that shock wave when it hits the ground. And you know, there's a front and that back end essentially is what creates the shock for, you know, the object traveling supersonically. And so the idea behind the X-59 aircraft is that if we change the shape, because it's the physical thing going that fast that causes the shocks to form, if you change the shape such that the shocks that propagate to the ground don't coalesce into your conventional N-shaped sonic boom, then you can potentially change that noise signature. And so that's what the X-59 uses, decades of research that's gone into it. So for instance, the nose of the aircraft is about a third of its length. There's actually not a forward-facing canopy. It uses a video system to look forward, but you know, the Concorde similarly had a long nose, and they had that whole, you know, lifting lower as it took off. We're not dealing with that. We're just going to allow it to be one piece of machinery that's not, you know, moving its nose up and down. But this, yeah, is one aspect that allows it to have the more smoother surface on the bottom. The engine is, you know, above the wings, and those are some of the components that allow it to a shock signature at the ground that is spreads that noise out over a longer period of time. And sometimes we describe it as a sonic thump rather than a boom.
You know, Boom Supersonic has this aircraft that's out, right? And I've seen on some posts where they have, it's boomless is what they call it. Now, as an acoustician who's studied a lot of times, right, we've studied a lot of different noise, percussive noise stuff, sonic booms as well. And so I sit there and I listen to it. I'm like, I would love to see the data, but no data has been presented. Is this aircraft much different? Like the X-59, is it much different than that aircraft? And the assumption that there's no sonic boom almost seems like it's kind of impossible, right? What's your thoughts on that?
Yeah, so the business model, Boom Supersonic, has said they're pursuing is transoceanic flights. There's no ban over water for sonic booms, and so their design is not utilizing the shaped boom technology that the X-59 aircraft is using. And
got it.
So they're not pursuing the low boom sound. They may have experienced Mach cutoff, but I don't know the specifics as to what is the rationale behind saying it's boomless when, you know, it's not necessarily using any quiet supersonic technology in the design of the aircraft as far as I'm aware.
So, for example, going back to the X-59, you were talking about as it moves through the air, you've got the front end of the aircraft, like you said, and you got the back end of the aircraft. So as it's traveling through, and it's got several wave fronts probably on the aircraft. Wavefront means like the pressure, right? The pressure gradient, the pressure differences. Would a listener hear one boom at the ear? Would it be multiple booms? Can you talk to a little bit about what that means?
So that's a great question. Some people say, why don't you just go fly supersonic over water, create the boom, and then fly over land? Well, the shock travels with the aircraft. It's kind of like the wake on a boat that travels with the boat. You know, wherever it goes, that wake follows, similar with this aircraft. And so, yeah, when you hear the sonic boom, generally you hear a double sound of pop up or something like that, because it's, yeah, the different surfaces create the pressure differences as you're mentioning, and essentially they coalesce, and you get that N-shaped wave form that people experience. So yeah, if you're just a singular location, you'll hear it, you know, pass by once. But yeah, that's the general principle there.
Cue in the N-shaped wave, because we're going to show that. So we'll explain what that means. There'll be a little thing there that we have for other impulsive sounds or whatever that gives you that. so that a listener can go, oh yeah, that makes sense. We
That's
think.
what he's talking about.
Yeah, that's cool. Okay, so with the X59, do we expect to hear the bop bop potentially, like two door closes or one single door, or do you have any idea on that?
They might hear it, they might not hear it. We have an interior effects room, which is a lab space that allows us to, I guess it has 52 subwoofers mounted on the wall, and the actual facility looks like a living room, and we bring participants in to listen to sounds, and those 52 subwoofers allow us to recreate the sound of a sonic boom, a conventional sonic boom, and this quiet supersonic noise signature, the sonic thump of the X59. And listening in, I took someone through a tour yesterday in there, and people almost didn't even hear if they were moving or making any noise. You might not even hear it potentially. And so
Cool.
That's the concept we're going into this with, that it's much quieter, and we need to fly the plane and test it out and make sure it is as we predict. But the technology seems to be indicating that it's going to be much quieter than your conventional sonic boom that the Concorde or other supersonic aircraft would produce.
That's awesome.
I was about to ask that question, is how do you guys kind of test this? Because I can't imagine it's cost effective to send that thing up every single time and run it.
Well, they're still on the ground testing,
They're
right?
still on the ground testing.
Right. They're getting it prepped. So when are we going to see it fly, you think?
Yeah, so the first flight is planned for this year, and after its first flight, we'll enter phase 2 of the mission, where we're going to validate the models. We have a lot of models that are going to help us in our phase 3 test, where we're flying it over communities to help predict the noise level. And so we need to go back out to the desert, Edwards Air Force Base, and make sure that that we're getting what we're expecting, and we can validate the models such that they're useful in our next phase to sync up the noise level individuals here in the community with their annoyance, and create that dose response data set to deliver to the regulators.
We talked a little bit about other business models and like the Concorde and things like that, and how why not just fly over the ocean, make the sonic boom, and then fly over land? Why not just follow that model? Why look at making this sonic boom less?
Yeah, so since the 70s, the FAA has prohibited overland supersonic flight due to the noise that is produced with the sonic boom. And so the goal here is to create this opportunity to fly quietly over land, to allow for more opportunities for, flying coast to coast. Imagine going from New York to LA in about 3 hours. That would be quite a significant reduction of time. I mean, my family lives all on the West Coast, and being able to visit them in much quicker time would be really amazing. So that's the goal that we're seeking here, is to collect the data necessary to inform the regulators so that they can make decisions that will have positive impact on the general public, and allowing for commercial supersonic to be a viable option.
So a lot of it is commercial purposes. I mean, obviously, you're kind of just getting that information, so then you can tell them this is what needs to be done to do that. I'm assuming. So it is for commercial purposes, and I'm sure there's a ton of other reasons that you could use supersonic travel.
This is one part of NASA where I'm just like so excited to see where this goes, because really it's like most people, they think space, and that just seems so far away. But an airplane, on the other hand, the majority of the U.S. public has flown, right, at some point. So this really can touch home to those. And the idea of flying supersonic, I'm going to ask you this question just because I think it's a silly question, but what do you think a listener would hear if they were sitting in the aircraft flying supersonic?
That's a great question. They wouldn't hear anything. They're traveling with the object going supersonically. They're not outside. They're not crossing through that shock. So, I mean, I'm not a pilot. There's others that I work with that are pilots, but even going supersonic, you watch The Right Stuff and see Chuck Yeager going through, and his aircraft is shaking and it looks like it's going to explode as he's trying to go through the sound barrier. But that's really not how these vehicles work. It is more energy to get through that transition of supersonic speed, but beyond that, you probably wouldn't even notice. It just,
once they hit the speed, it's relatively quiet. It's whatever's in the cockpit is rattling. So is all your data that you've taken so far, obviously you're doing the environmental impact kind of portion of this, right? It sounds like you're spearheading for the X59. Eventually part of your job will be public reaction, but no interior or aircraft, that's going to be all Lockheed. I just want to make sure that is that true?
Yeah, so Lockheed is building the aircraft, and then they'll deliver it to us, and we'll be flying it over communities and
Cool.
through surveys, requesting annoyance responses to the flyover events.
We're going to throw it out there. Let's throw the 100-year question out there. Okay, you were talking about electric vehicle vertical, so we'll get into that in a second. But let's talk supersonic. 100 years from now, are we flying supersonic all across the United States and the world?
Yeah, I would imagine that in 100 years, the technology and everything would be in a place where we could travel coast to coast in much quicker times. There's even ideas out there of hypersonic travel. We're not tackling that. Hypersonic is, Mach 5 times the speed of sound and above. We're not tackling that problem right now, but there's folks out there that are thinking about that as well. And so, we're going to work through this en route supersonic noise problems that becomes viable, and we'll see if we can achieve even faster speeds beyond that.
And then one more thing, because we're sitting here in a lab right now, right? So this is our anechoic chamber, and you talked about a listening lab where you bring folks in and they listen. Can you talk just briefly a little about some of the labs you guys are using? Is that just the only one, or what else do you guys have?
Yeah, so we have some anechoic chambers here as well. I primarily work with the interior effects room and exterior effects room. The interior effects room we use for mostly sonic boom like sounds, where we have the 52 subwoofers that enable that low frequency reproduction to really get that sound produced. Then the exterior effects room, it's more like a small auditorium where we have several, about 30 speakers throughout the room that allow us to play back recordings or auralizations, which are synthesized sounds based off of the physics and geometry of vehicles, to play those eVTOLs or other vehicles in motion to allow us to capture the effect of that vehicle and in a more realistic environment.
Oh, that's
Though
cool.
It's not the actual vehicle, it's a recording or auralization in that environment.
So that's cool. So you do the playback in that kind of like surround sound-esque, but beyond surround sound, because most of that's like 7.1 or whatever it is, or 7.2. This is like that full 3D effect. One more thing. So Tag Durant, he was on this a while ago. Were you part of some of the research you did where they go out, because you were talking about sonic boom, so I'm assuming you've taken several acoustic signatures of other aircraft where you fly them in a certain configuration and you try to get them to do different types of sonic booms, because like obviously pitch, yaw, all the fun things that an aircraft can do, that changes the signature of a sonic boom even if it's already flying supersonic, right? So was that part of the program you had worked on previously?
So I haven't had the opportunity yet to participate in a NASA field study, but I've analyzed a lot of data from Quiet Supersonic Flight 2018, which was conducted in Galveston, Texas, and there was another campaign that was near Edwards Air Force Base. Both of those were demonstrating quiet supersonic noise signature through a low boom dive maneuver of an F-18. That allowed us to demonstrate, proof of concept of collecting that dose response data to quieter noise signature that helped us develop a lot of the methods that we're using. So I haven't participated in that yet. In grad school, I went out and measured an as a Falcon 9 that was near Vandenberg Air Force Base, and that was an amazing opportunity to go out and collect that data and to experience the triple boom that those Falcon 9 boosters produce.
Cool.
Mark Anderson at BYU recently published a paper that explains why they have the triple boom as in contrast to this double boom that most supersonic objects produce.
That sounds like exciting technology. I know that I've seen in the past, like this is kind of the big next front, I would assume. There's been a big push and drive for that. Talk to us a little bit about your program there. What are you doing on that front?
Yeah, so the project at NASA I work on is the Revolutionary Vertical Lift Technology Project that works with advanced air mobility vehicles. These are made up of these electrical vertical lift and takeoff, which are eVTOLs. They range from drones that are called SUAS or small UAS, the small uncrewed aerial systems, to these UAM urban air mobility vehicles that are intended to be transporting people and cargo in urban environments. And so air taxis is this new emerging technology that is anticipated to appear in some of these larger cities in the near future potentially.
Air taxis and drones, which we love drones, right? And the drone noise is problematic, right? I mean, to some extent, I think folks don't want to hear drones. Is that a fair assessment? I mean, not that your opinion's the end all be all, but I'm assuming that there's a reason that you were part of this program, and that's to dive into this.
Yeah,
correct?
so some of my colleagues, they published a paper that was comparing drones with transportation vehicles, ground transportation.
Oh, interesting.
And it was, definitively different annoyance response, that the drones were more annoying. And, that was 2017 or so that they did that study. And now we're more focused on these UAM, urban air mobility, air taxi-like vehicles, as they're, several companies are approaching, certification, and they're doing demonstrations. You can see them on YouTube and elsewhere. And, Paris Olympics, they had some air taxis that were demonstrated there. The Osaka Expo this year, they've got some air taxis they're demonstrating. The LA Olympics as well will probably be a venue where you may see some air taxis being demonstrated.
I would assume so. That's cool. So when do you think, I mean, is there a timeline, not that you're these companies, but is there a big push? I got to think there's a lot of, I don't want to call it red tape, but obviously a lot of certifications and all that stuff. When do you think like we might see these things flying around consistently? Not like the first, are we talking 25 years out? Am I going to be an old person, or am I going to still, be young enough to enjoy this,
Well, at NASA, we partner with industry and other government agencies and academia as we do this type of research on these new vehicles. I personally don't know exactly the timeline that they're all looking at. NASA does not do certification or regulation or policy, but we conduct the research to help inform those decisions that folks with that responsibility. And so I imagine it's coming up. You can find articles online that talk about various companies at various stages of development with their aircraft. Some of them are flying actual aircraft now. So awesome. I don't know. It's beyond my expertise as to the certification regulation process, but they're pushing on it.
What you said like annoyance. So you talked about ground, like in 2017, the study, you said, hey, there's more annoyance associated with drones as opposed to ground transportation. Like this kind of dives into the realm of psychoacoustics a little bit. So you guys are doing that research. I mean, this is perfect because there's a lot of people who are annoyed with all sorts of noise, right? It doesn't have to be aerial drones or whatever. But how do they do these types of studies? How are you deciding? Maybe you're characterizing some of the noise right now, or you're going through these listening rooms, like you're saying, the interior versus exterior. Can you walk us through kind of like that process of what is that like?
Yeah, so our laboratory tests are opportunities to focus in on a particular question. Obviously, it's not a lived-in experience when we have people come into the lab and listen to sounds and rate their annoyance, but it can give us information as to what things people key into when they hear a sound. So obviously, how loud something is generally the most predominant factor in someone's annoyance response, but we found with UAM vehicles and drones as well that there's sound quality metrics that can help dive into other aspects of the sound, the tonality, the roughness, the sharpness, the fluctuation strength, that can also be secondary contributors to the overall annoyance. And so we are able to use the lab studies to help us figure out, what is causing people to respond in certain ways, and we can then build upon that. And eventually we're looking to do community studies as well, because we really need to do that lived-in experience type test to know how people in the communities will respond to these type of sounds, so that we can inform regulators and provide them the data that will allow them to make the appropriate decisions.
Now, for anybody that hasn't experienced, most people probably experience small drones. Obviously, we probably all have heard those. But for like an air taxi, I mean, are we talking the sound of a helicopter? Or if they've got like 5, or let's say they got, 8 blades on this thing smaller versus one, big and a tail blade, is it 3x, 4x louder? I mean, can you talk to us? I mean, how does the sound kind of compare roughly?
That's a great question. That's exactly what I'm working on right now. Summer 2025, we're planning to do a UAM comparison with helicopters, because they're both rotorcraft and somewhat similar size, the lightweight commercial aircraft and these air taxi, UAM vehicles. But yeah, exactly. The rotor blades are much different. There's generally more on the more smaller ones on the UAM vehicles than the helicopters. And so we anticipate there to be specific differences, and we need to kind of figure out, what is the annoyance response? How do people differentiate between them? There's relatively few studies that start to look into this, but not as in depth as we're planning to go, with looking at several different vehicles and looking at a couple different configurations as well, to really understand, how do people respond to these different vehicles? People don't respond to air vehicles the same way as they do to road transportation. There's differentiation. In early days of community noise studies with the Shulz Curve, it was conglomeration of all those things, but recent studies such as the Neighborhood Environmental Survey that the FAA did, they found that people respond very differently to aircraft than they had previously supposed based off of that data set from the 70s.
What's the Shulz curve?
Basically, it's the first community noise study that it showed the annoyance as the dose response, noise exposure versus the annoyance, and it was a conglomeration of several studies of various vehicles and different communities, and that's the baseline in community noise studies.
Cool. So that's where it all started. That's where it all started, and from there you're working your way up. That's cool. Yeah, I'm learning some things that I didn't know, right? Because it's obviously there's a lot I'm learning here. So I hope you're learning too, Robert.
Or so much stuff that I'm like,
he's like, it's too much.
It's so much I never even thought about. That's the thing, is I'm sitting here thinking this whole entire time, about the air taxis and things, and it kind of made me think. So what's our future of flight, right? We talked about a helicopter. Helicopter has one blade, one in the back. It's also gas powered.
He's calling them rotors, so just to make sure we are using the wrong terminology already.
I know there's particulars about propeller and other things that I'm not fully aware of, so I'm not an expert.
I'm a simpleton, all right.
I take the noise and evaluate the noise. I'm coming up to speed on the geometry and physics of it all.
Yeah, there you go. We don't want the aircraft, the engineers going, it should be impeller, it should be rotor, it should be this.
And all those aircraft engineers can come at me, because I say, listen, sonic boom, it goes boom. That's what I know. I'm not the smartest here, but my thoughts are this: are we looking at and a lot of talk happens about gas powered compared to electric. We're looking at electric vehicles. Are we looking at electric flight? Are these taxis electric? Because there's some noise that comes from those engines compared to, say, an electric car, right? So, is that where we're kind of going with these things?
That's what he was saying on the electric vehicle. So you're asking him,
do we think that at some point we'll have supersonic flight using electric flight?
Using electric battery powered motors.
That's beyond my expertise. I'm not much of an emissions person, or I'm really focused on the noise side of the problem, of the challenges that the noise produces. But yeah, I think that there's always NASA seeks to make transportation safer, faster, cleaner, and our focus is making it quieter.
So when you say, really quick, when you say, so you're analyzing all these aircraft, right? Whatever it is out there, and these maybe concepts and whatnot. Do you ever, beyond just analyzing them or validating, do you validate the data that they provide too, or is it just more of like community response? And the reason I'm asking this is because, do you ever say, oh man, you've got this 3-foot diameter fan, okay, a rotor with this type of design, you really should be changing it up, or you don't get into that. You're just saying, we evaluated it, here's what we see, and we're going to compare it to this other one, and here's what we see, and we're going to compare it to this other one, and here's what we see. You see what I'm saying?
Yeah, so our team is multifaceted. We have folks that are working on generalizing noise based off of the geometry and physics. They're doing auralizations or simulations, synthetically generating the sound. There's others that are looking at characterizing the noise sources, and I guess myself and a couple others are more focused on that human aspect of how do we respond to the sounds. But I try to do what I can to understand the physics and understand where is the sound coming from, because if we can figure out hey, what is the mechanism by which people are responding to? What is generating that particular frequency or component of the sound that people are responding to that can inform others, so that manufacturers can take that information and incorporate it into their design. That's these eVTOL vehicles are utilizing these technologies that we have to incorporate the perception into their design to influence that you don't have to build an entire aircraft, test it, and then figure out, oh, it's way too annoying. That's not the process here. It's that we have the capabilities to use the geometry and physics to generate the sound and evaluate
so you're doing
it.
simulation, like you're saying auralizations. You're actually doing some simulation there.
Yeah, we do auralizations. We use recordings. We use what we can, and we've gone through validation with some sounds, but with new noise sources, we need to go through validation. So there is an aspect of validation that we perform as we work through these challenges.
Got it. One thing you said to me that really kind of struck out is because it struck out to me, or strikes me, is that you said, you're still determining the perception, right? Like that's kind of where your expertise lies right now at NASA. True?
Yeah. So we have folks from the local area that we bring in on center, and they're paid participants in these studies. And yeah, I've had to learn a lot of statistical modeling.
You learned all about the correct, and this is not the world I live in, but the correct statistical approach, so that you guys can't say, oh, you guys skewed the data this way or that way. There's statistics and a method associated with this.
Yeah, so when I was hired on at NASA, they were considering whether to hire a statistician that they taught acoustics or an acoustician that they taught statistics. I'm an acoustician. I never took a dedicated statistics course in my college experience, but several physics courses touched on the topics of statistics in various ways. But that was something that was challenging and hard for me at first, was coming up to speed in an area that I just had very little practical experience. My older brother, he's a statistician at Nike, so I was able to talk to him a little bit as I was interviewing and trying to figure out what are they talking about with these statistics things. But since onboarding at NASA, I've been able to rely on our teammates that are statisticians and really learn a lot from them and
cool.
Come up to speed to an extent. But the nice thing at NASA is that you don't need to be the smartest person in the room. You don't need to know everything. There's several people with great expertise that you can draw from and learn from and produce a better product than you would on your own, and learn a lot along the way.
I love that you're saying you basically have mentors within you all can mentor each other, and you got that huge bandwidth of experience. Do you see, I kind of feel like this is in some ways the passing not of a decade. You've got 40-year veterans retiring, and there's a huge transition. I feel like I'm not inside NASA obviously, but is there any truth to that at all? Do you see you got folks who've been there for their whole careers, and now as the younger generations kind of come up through the ranks, it's how do we transfer this wealth of knowledge and all this experience onto the younger generation? Is that a fair assessment? I would assume so.
Yeah, I think there's always a need to have that knowledge transfer, and within the acoustics branch, we're very fortunate to have several different people in different stages of the career, and we're able to, I've been here for almost 5 years now, and I've learned a lot from the more experienced members, and so there's a natural organic way that happens, but also we take dedicated ways of documenting our research, and so that the next group can come along and pick it up. But it's, these projects have longevity such that those expertise continue throughout, regardless of personnel changes along the way with retirement and things that happen in life.
Yeah, that kind of touches on something I wanted to ask you, seeing as how you've worked there for 5 years, so you're not super far removed from being in the academic world and going to school. If I was a college student right now in acoustics or something of that nature and wanted to go work for NASA, what kind of advice would you give somebody like myself who says, this is what I want to do, now what do I need to know? What's the pieces of advice you'd give?
Get involved in research. Start early. As an undergrad, if you have opportunities to do research with successful professors that are actively publishing and presenting their work, that's invaluable experience. I had the privilege to work with Dr. Kent Gee, who does a lot in nonlinear acoustics, from jet noise to rocket noise to sonic boom and other various sounds. And that was a great experience to learn the technical writing process as a student and to learn how to present as well. Those things were invaluable. Technical communication is key, and you want to develop those in an academic environment where there's a focus on learning and growing. There's always learning on the job as well, but as much as you can do before you get out into the workforce in that educational environment, it's so much more impactful and valuable for you to come into the workforce with those key skills that are requisite for a researcher.
And I talk about the 100-year goal here. I talk about it like big numbers, not 25 years down the road, but like ultimately, like we're thinking 2, 3, 4 generations beyond you. Does NASA have like those big goals?
Yeah, so the first A in NASA is for aeronautics, and that's been something that we've been doing here at Langley Research Center before NASA was even conceived of. And so they're going to continue working on making aviation to be safer, cleaner, more efficient, and faster. So I think those are some of the key pieces, and our role in there as acousticians is to help make it quieter. And that's what we're about, is making it so that it's more accessible to everyone, and NASA innovates for the benefit of humanity. And that's something that really drew me into this work, that it would be something that would impact everyone out there and the next generations to come.
Well, thank you for coming on our show, and we appreciate your time, Aaron. Thank you so much.
Thank you. I appreciate it.
Thanks for coming on. We really do appreciate it.
All right.